Good morning, everyone. Today we move deeper into vehicle dynamics. Specifically, we will understand the Earth fixed coordinate system, dynamic axle loads, and how to formulate the vehicle equations of motion. Whenever a vehicle accelerates, brakes, or corners, forces and moments shift between the axles. Understanding this weight transfer is fundamental to predicting handling, stability, steering feel, and even crash performance. An inertial Earth-fixed coordinate system is required to write Newton's equations for vehicle motion. Measuring acceleration relative to the ground allows accurate prediction of vehicle behavior. This includes weight transfer, stability, and control during braking, acceleration, and cornering. Using the Earth-fixed frame ensures that vehicle dynamics correctly represent real driving conditions on the road. Let's begin with how vehicles are represented mathematically in an Earth-fixed inertial frame. In physics, motion is always measured relative to something called a reference frame. In vehicle dynamics, Newton's laws only apply in an inertial frame, which means a frame that is not accelerating. For road vehicles, the Earth is close enough to an inertial frame. So vehicle motion is described relative to the Earth, not relative to the vehicle itself. This is called the Earth-fixed or global coordinate system. In this frame, the x-axis points forward along the road, the y-axis points across the road, and the z-axis points upward. This fixed coordinate system is used to describe the true motion of the vehicle in space. The vehicle's position is described by the location of its center of gravity. This position changes with time and is written as x of t, y of t, and z of t in the Earth-fixed frame. Velocity is the rate of change of position with time. For road vehicles, vertical motion is zero because the vehicle stays on the ground. So, motion is simplified to two dimensions, with forward velocity and sideways velocity only. Acceleration is the rate of change of velocity with time. Since there is no vertical motion, vertical acceleration is also zero. Newton's second law states that the sum of all forces equals mass times acceleration. This law is valid only in an inertial frame, like the Earth-fixed frame. Therefore, all forces acting on the vehicle, such as tire forces, braking, aerodynamic forces, and gravity, must be related to acceleration measured in the Earth frame. The Earth-fixed frame is physically correct, but it is not always easy to use for vehicle modeling. Forces from the tires, steering, and vehicle body act in directions related to the vehicle, not the road. Because of this, describing these forces in the global frame can be complicated. To simplify the analysis, a vehicle fixed or body coordinate system is used. This frame moves with the vehicle and has its origin at the center of gravity. Its axes are aligned with the vehicle's forward and sideways directions. Using the vehicle fixed frame makes force calculations, control design, and vehicle modeling easier and more intuitive. The vehicle fixed frame is attached to the vehicle and moves and rotates with it. Its origin is at the center of gravity. The x-axis points forward, the y-axis points to the left, and the z-axis points upward. Because this frame aligns with the vehicle, longitudinal and lateral velocities can be measured directly. This makes tire forces, steering effects, and vehicle dynamics easier to analyze. A rotation matrix called r of theta is used to map vectors from the vehicle frame to the Earth frame for planar motion. The angle theta of t represents the vehicle's orientation at each instant in time. The matrix R is orthogonal, which means its inverse is equal to its transpose. Both R and R transpose are written as clean 2x2 matrices. These matrices form the mathematical foundation for transforming velocities and accelerations between the body frame and the Earth frame. Earth frame velocity and vehicle frame velocity are related by the yaw angle, psi. This relationship is described using a rotation matrix, R of psi. When the matrix is expanded, we obtain the velocity equations. Vx equals u cosine psi minus v sin psi. Vy equals u sin psi plus v cosine psi. This transformation is purely geometric. It shows how the vehicle's forward and lateral velocities are projected onto the fixed Earth axis. These equations come from rotation matrices and allow us to move between physical motion and vehicle-based dynamics. Body frame velocity is written as Vb equals uv. Earth frame velocity is obtained by rotating this vector using the rotation matrix. The relation is Ve equals r times Vb. Expanding the matrix multiplication gives the component equations. Velocity in Earth frame along x equals u cosine theta minus v sine theta. Velocity in earth frame along y equals u sine of theta plus v cosine theta. These equations show how forward and lateral speeds in the vehicle frame are converted into inertial earth frame velocity components. Earth frame acceleration is obtained by differentiating the earth frame velocity components with respect to time. The product rule is applied because both the velocities and the orientation angle depend on time. After differentiation, the terms are grouped to collect u dot, v dot, and theta dot. This results in the earth frame acceleration components AEX and AEY. Each component contains both translational terms and rotation-related terms. This step prepares the equations to be separated into body rate and rotational contributions. Earth frame acceleration can be written in a compact matrix form. The equation is AE equals R times U dot V dot plus omega J times UV. Here omega equals theta dot, which is the yaw rate, and J is the 90-degree rotation matrix. The rotation matrix R maps the combined body frame acceleration and Coriolis term into the inertial frame. Writing the equations in this form makes the structure clear and prepares the expression for inversion or further analysis. Body frame acceleration can be obtained from earth frame acceleration by multiplying with the transpose of the rotation matrix. This gives the relation a B matrix equals U dot minus omega V and V dot plus omega U transpose. In this expression, U dot and V dot represent the raw acceleration measured by sensors fixed to the vehicle. The terms minus omega V and plus omega U are correction terms caused by the rotation of the vehicle frame. These corrections are required to remove Coriolis effects and recover the true inertial acceleration. This completes the two-way transformation between earth frame and body frame dynamics. What is the physical meaning of the omega terms in the equations? These omega-related terms come from differentiating sine and cosine functions, not from any abstract mathematical operator. The terms minus omega v and omega u represent transport acceleration, seen by a rotating observer. They appear because the vehicle fixed frame is rotating with the vehicle. Sensors mounted on the vehicle naturally measure these extra effects. To obtain the true motion of the vehicle in the earth frame, inertial measurement systems must compensate for these apparent forces. Let us summarize the key acceleration equations used in planar vehicle motion. The first equation gives acceleration in the earth frame. Acceleration in earth frame equals R times VB dot plus omega J VB. The second equation gives acceleration in the body frame. Acceleration in body frame equals VB dot plus omega J VB. These two equations have the same structure and are closely related. Together, they show how acceleration measured by body-fixed sensors can be translated into inertial earth frame acceleration. Understanding these compact equations makes it easy to move between earth observers and vehicle-based measurements in guidance and motion analysis. When the transformed acceleration is substituted into Newton's second law, we obtain the final body frame equations of motion. The longitudinal equation is m times u dot minus vr equals the sum of forces in the x direction. The lateral equation is m times v dot plus ur equals the sum of forces in the y direction. These equations show that the accelerations measured in the vehicle frame are not purely inertial. The rotational terms ur and vr must be included to correctly represent the true forces acting on the vehicle. These are the complete and correct body frame dynamic equations. Even though the equations of motion are written in the vehicle frame, they always start in the inertial earth frame. The equations are m times u dot minus vr equals the sum of forces in the x direction. M times v dot plus ur equals the sum of forces in the y direction. The extra terms vr and ur appear because the vehicle frame is rotating and is not inertial. Including these terms keeps the equations physically correct, while still allowing analysis in vehicle-based coordinates. Longitudinal motion is described by the following equation. M times u dot equals the sum of fx minus mvr. Here, u is the forward velocity of the vehicle. The term sum of fx includes traction, aerodynamic drag, and rolling resistance forces. The term mvr represents the coupling between longitudinal and lateral motion. This equation is the first of three coupled differential equations that describe planar vehicle motion. Lateral motion and yaw motion are described by a coupled pair of equations. The lateral equation is m times v dot equals the sum of Fy plus mur. The yaw equation is Iz times r dot equals a times Fyf minus b times Fyr. These equations show how lateral velocity and yaw rate are linked to forward speed, steering input, and tire cornering stiffness. Together, they determine the vehicle's path and its stability during motion. The steering angle delta is the angle of the front wheels relative to the vehicle's forward direction. It is a direct driver input and exists even when the vehicle is not moving. By itself, it does not create tire force. The slip angle, alpha, appears only when the vehicle is in motion. It is the difference between the wheel's pointing direction and the actual direction of tire motion. Slip angle comes from tire deformation and determines the lateral force that turns the vehicle. #bicycle model ground rules. We adopt a linear bicycle model assuming small angles, constant longitudinal speed u, and negligible tire saturation. These simplifications let us write alpha approximately equal totan alpha and treat cornering stiffness CF, CR as constants to relate slip angles directly to lateral forces. To find the lateral velocity at the rear axle caused by yaw rotation, we evaluate the cross product omega cross r. The angular velocity omega is the yaw rate r acting in the vertical k direction. The rear axle position vector points backward along the vehicle and has magnitude b, so it lies in the negative y direction. Taking the cross product of rk hat with minus bi hat, and using the basic rule that k hat cross 1 hat equals j hat, the result simplifies neatly. The final vector is minus b times r in the j direction. This shows that yaw rotation creates a pure sideways velocity at the rear axle, with magnitude br pointing laterally across the vehicle. We begin with the angular velocity vector omega equal to r in the k direction. Using this definition, we evaluate the cross product step by step. This vector operation directly produces a lateral velocity term equal to minus b times r. When this rotational contribution is added to the vehicle's lateral velocity v, the rear axle lateral velocity becomes v sub r equals v minus br. No matrices or complex algebra are required. This clean vector approach shows how yaw rotation alone creates sideways motion at the rear wheels, allowing us to predict rear wheel behavior during turning using basic angular motion principles. At the front axle, the lateral velocity is v plus a times r, combined with the forward speed u. This gives the front slip angle as alpha f approximately equals delta minus v plus a times r divided by u. The front slip angle depends on both the driver's steering input and the vehicle's motion. This slip angle generates the front lateral tire force, given by Fyf equals Cf times alpha f. The rear axle experiences a lateral velocity of v minus b times r. This leads to the rear slip angle, written as alpha r approximately equals minus v minus b times r divided by u. Unlike the front tires, the rear slip angle does not depend on the steering angle delta. It is determined only by vehicle side slip and yaw rate. As a result, the rear lateral tire force is given by Fyr equals Cr times alpha r. For small slip angles, the lateral tire force is proportional to the slip angle. This relationship is written as Fy equals C times alpha, where C is the cornering stiffness. This linear model simplifies complex tire behavior into equations that are easy to use for vehicle dynamics and control. By combining the slip angle expressions with Fy equals C alpha, the front and rear tire forces Fyf and Fyr are obtained. These equations show how the steering input delta and the vehicle motions Vr and U together determine the lateral forces at the front and rear tires. A linear tire model is used to describe the lateral forces generated by the tires. The front lateral tire force is given by Fyf equals Cf times delta minus V plus A times R divided by U. The rear lateral tire force is given by Fyr equals Cr times minus V minus B times R divided by U. Here, C sub F and C sub R are the cornering stiffnesses of the front and rear tires. These equations link the steering angle, vehicle velocities, and yaw rate to the lateral tire forces. The resulting forces are then used in the lateral and yaw equations of motion. From the equations, we can interpret that the driver's steering input directly controls the front tire force. The rear tire force is created by the vehicle's motion, not by direct steering. Forward speed u appears in the denominator of the equations. This means that at higher speeds, slip angles become smaller. As a result, more steering input or yaw rate is needed to produce the same lateral force. Newton's laws are valid only in the earth-fixed inertial frame. This is where true physical motion is defined. However, vehicle forces in geometry are easier to describe in the vehicle-fixed frame. So, vehicle equations of motion are derived in the earth frame first. They are then transformed into the vehicle frame for practical analysis. In short, physics lives in the earth frame, and vehicle dynamics is a transformed version of that physical truth. The core insight is that taking the time derivative inside a rotating frame injects extra terms, precisely Vr and plus or, because the frame itself is spinning. These terms are not forces but kinematic corrections that account for the rotation rate. Velocity can be transformed between the earth-fixed frame and the vehicle-fixed frame using the heading angle, CSI. Earth frame velocities Vx and Vy are related to the vehicle frame velocities u and v through this rotation. In a numerical example, the earth frame velocities are Vx equals 20 meters per second and Vy equals 2 meters per second, with a heading angle of psi equals 10 degrees. Applying the coordinate transformation gives a forward velocity of u equals 20.04 meters per second and a lateral velocity of v equals minus 1.50 meters per second. This example shows how velocities are converted between reference frames using the vehicle orientation. This example shows how velocities and forces are transformed from the vehicle frame to the earth frame. The vehicle has a forward speed u of 20 meters per second and a lateral speed phi of 2 meters per second. The yaw angle is 30 degrees. Using the transformation equations, Vx equals u cosine psi minus v sine psi, and Vy equals u sine psi plus v cosine psi, with cosine 30 degrees equal to 0.866 and sine 30 degrees equal to 0.5, the earth frame velocities are Vx equals 16.32 meters per second and Vy equals 11.73 meters per second. The same rotation applies to forces, with body frame forces Fx equal to 4,000 newtons and Fy equal to 1,500 newtons. The earth frame forces become Fx equals 2,714 newtons and Fy equals 2/3 how velocity and force components in the vehicle frame rotate into the fixed earth frame using simple trigonometry. Let us solve a potential problem to understand the need for the transformation. Let's take the problem provided to us with data of initial velocity, yaw angle, yaw rate and forces acting on the car like drag, rolling resistance, traction, front and rear tire, lateral force, braking forces. We are to compute the net longitudinal and lateral forces in the body frame, compute the body frame accelerations and transform the acceleration into the earth frame, and finally compute the earth frame velocity after 1 second. The first step is to compute the net longitudinal and lateral forces in the body frame. Drag, traction, braking, and rolling resistance forces are combined to obtain the net longitudinal force. Lateral tire forces are summed to determine the net lateral force in the body frame. Next, the body frame accelerations are calculated using the applied forces. Using the equations of motion derived earlier, the longitudinal acceleration is determined by assuming that the lateral velocity 5 equals 0 at the start. The lateral acceleration in the body frame is also computed. These body frame accelerations are then transformed into the earth frame using the rotation matrix and the yaw angle. Finally, the earth frame velocity of the vehicle is computed after 1 second. Using simple vector analysis, the magnitude of the velocity is calculated. The direction of the velocity is also determined with respect to the earth-fixed frame. This provides a complete description of how fast the car is moving and in which direction it is traveling in the inertial frame of reference. In summary, today we established the foundation for vehicle motion analysis. We defined the earth-fixed frame, explained its relationship to vehicle-fixed velocity components, derived dynamic axle loads, and developed full equations of motion, including yaw dynamics. With these tools, engineers simulate braking stability, cornering limits, rollover risks, and control strategies for ABS, ESC, and autonomous vehicles. In our next session, we will apply these equations to a real-time vehicle problem.